working. Welcome to my talk. I'm Till. Today I'm going to tell you a little bit about fault tolerance and job recovery in Apache Flink. So I've heard that we don't have much time, so let's get started. What happened there? Well, damn it. It's wait. There it's written Windows, so I'm running on a Mac, so it can't be me. So I'm fine. So I'm quite sure every one of you has seen this kind of failure. Many different failures. Failures in general happen at various times. They appear in various forms. But there's one thing which is sure about them. They will happen eventually. EMC actually estimated that in the year 2014, there were costs inflicted by data loss and system downtime, which amounted to 1.7 billion system. So as a company or as a user, you would want to use a system where no failures happen, ideally. Or, since this is kind of hard because failures will happen, a system which can recover from these kind of failures quickly. If you have a system which can recover from failures, it actually means that it can draw some kind of checkpoints of the intermediate states from which it can continue working again. Actually, if you have this kind of mechanism, you can also do some other cool stuff with it. Like, for example, applying different algorithms. Like, assume you have a prediction pipeline with an online learning algorithm where you have learned a kind of model. And now you've found out that you've actually can improve the accuracy by using a different algorithm, but which works in the same state. By simply drawing a checkpoint from the state and starting the job with this new algorithm from this point on, you can basically benefit from the, can avoid recomputing the complete model. Another cool thing would be a live upgrade of your system. Assume there's a new version of Flink out there, and you want to update to it, but you don't want to stop your job. Then you simply start up some instances with the new system and let them take over from the latest checkpoint you've made. But now let's take a look at fault tolerance first. So when we talk about fault tolerance, we have to distinguish between different guarantees the system can give you. In the streaming space, we have three guarantees. Like they are ordered here from the weakest to the strongest. So the weakest guarantee is at most once, which actually says there's no guarantee at all. So either you see the element or you don't see it because your system crashed. But in any case, you will see it at most once. A slightly more useful guarantee is the at least once guarantee, which says that you will see every element in your stream or event at least once. So assume you have a counter, for example, which counts the elements you've seen. Then this counter will give you an upper bound to the real elements you've seen. So it might happen that in case of a failure, some of the elements are replayed and you've counted them twice. But for many applications, this kind of guarantee is enough to produce good results. The strongest guarantee for fault tolerance is exactly once. Exactly once says that every element is accounted for in your final state or result of your computation exactly once, which not necessarily means that you haven't processed it exactly once, because in case of a failure, it might happen that you switch back to a checkpoint where you haven't processed this element yet. But before the failure, it might have been that you just processed it. So in that case, you would reprocess it, but in the overall result of your state, it will only be accounted for once. The good thing is, or the good news, that Flink gives you all of these three guarantees. So you can choose, depending on your need, which guarantee you want to have. Okay, when we talk about taking snapshots for or checkpoints for fault tolerance of a distributed data flow, it's not so easy. You can think of taking a picture of a flock of gnus which runs over some grasslands, but not only from one position, but from multiple positions. And to make the whole thing a little bit harder, you and your friends don't have like synchronized watches, so you can't use time to trigger when to take the picture. So you need some kind of other mean to tell your friends when to take a consistent picture of the whole scene. This mean in the world of Flink is what we call barriers, which are markers which are injected in the data stream, where also your elements are streamed from one operator to the other operator. The barriers, since in a data stream elements can't overtake each other, including barriers, barriers basically tell you which elements belong to the current checkpoint and which elements belong to the next checkpoint. So once an operator receives such a barrier, it knows, now I've seen all elements which belong to my current checkpoint, so it can draw a snapshot of it, emit this barrier to my downstream operators, and continue processing. The cool thing about these barriers is actually that they flow with the elements, and thus there can be multiple checkpoints being taken in your data flow. Of course, not by the same operator, but by different operators. For a single input operator, it's quite straightforward how to handle these kind of barriers. As I've said, you see the barrier, you draw the checkpoint, and then you create a new barrier at the outputs. In case of a multi-input operator, like a join operator, for example, or after a shuffle, you have to wait for the barriers from all your inputs before you can draw the checkpoint and emit a corresponding barrier on your output channel. In case that one of your inputs should be a little bit slower than the other, this means if you want to have exactly one semantics, that you have to block the processing of the inputs from where you already have received your barriers. This means like buffering them up and waiting until you have received all barriers. Once you've done that, you can draw the checkpoint again and emit a new barrier to the outputs. And then the whole processing just continues, including the buffer elements, of course. If you can live with a slightly weaker guarantee, the at least once, for example, or in this case exactly the at least once guarantee, then the system can be a little bit more, or can avoid this alignment by simply processing elements which also arrive after the the checkpoints, after the barriers. So if one of some of the inputs you've already received the barriers, then you simply continue processing also those elements without buffering them. But again, you will only emit and draw the checkpoint and emit the barrier once you've received all barriers from your inputs. This, of course, means that your checkpoint which you will create will contain some of the elements which are part of the next checkpoint. Thus, there's the at least once guarantee, which you basically get by doing so. Okay, now we've seen how to, or how we can achieve that the operators know when to take the checkpoint. But what is actually included in the checkpoint? Well, in Flink we have different operators. There are the stateless operators, like a simple filter or map operation. They're stateless, so we don't have to create any snapshots of it. Then we have operators which have system state, like operators which create windows. So whenever a checkpoint or a snapshot is supposed to be drawn, you also have to include the current states of the windows you're constructing at this operator, because in case of a failure, you want to reconstruct it, right? Otherwise, your failures won't be the same. The windows won't be the same, sorry. And last but not least, we have the user-defined state, which is can be part of user-defined functions. And here, at the bottom of the slide, we see a reduce function, which simply sums up the long values which come in, and additionally counts how many elements have been reduced. To make the system aware of the user state, we use this operator state type here. By doing so, the system knows that in case of a checkpoint, this state has to be stored somewhere, so that when a job is recovered, it can be retrieved via this statement in the open method. That way, this state is checkpointed. Okay. Since all theory is gray, let's take a little bit more complete example of the algorithm. So first of all, I have to give a rather important note. In order for this whole fault tolerance checkpointing system to work, we need sources which can be replayed, at least to some extent. So, for example, the Kafka sources have a kind of offset to which you can rewind the stream so that you can replay parts of the stream. So we need sources which have a kind of position in the stream to which you can go back in case of failure. Okay. The checkpoints are triggered by the master or the checkpoint coordinator. The checkpoint coordinator sends a message to all sources, which will trigger the execution of the checkpoint. So once the sources have received this message, they will report back the current position or offset in case of, if you use the Flink Kafka connector, to the master, and emit a barrier to the downstream operators. That's what's happening here. Once an operator has received the barriers from all its inputs, it knows that it now can draw a checkpoint. Since the user state, or the checkpoint can be quite large. For example, consider you're constructing some kind of NLP model in your operator. Then you don't want to send it back to the job manager, but you rather persist it on some state backend, which in our case, or in many cases, would be like HFS, for example. The handle to this state is then sent back to the master where it is recorded. Once this is done, a new barrier is emitted to the downstream operators. In this case, from here to here. Okay, this goes on until all sinks have received the barriers from the inputs. And once a sink has received all barriers, it will acknowledge this checkpoint to the master. And once the master has received all the acknowledge messages from the sinks, it knows that a state is complete, or the checkpoint is complete. So now, once you've done that, it's rather trivial to restore from a failure, right? So the only thing you have to do is you have to retrieve the latest checkpoint, completed checkpoint. You have to reset the sources with the recorded position in the stream, and initialize the different operators with their state. And then you have to kick off the execution again, and yeah, it starts doing the job again. Okay, what are the advantages of this approach? Well, first of all, the checkpointing mechanism is completely orthogonal to the application logic. So it's not bound to any window sizes or micro batch sizes. It's up to the user. It can be an arbitrary interval. It can also be triggered manually, for example. And this gives you the freedom to tune your job also for different parameters you might be interested. For example, high throughput. So, for example, you could decrease or increase the interval between checkpoints to decrease the offset, or the overhead of checkpointing, for example. Furthermore, since only a barrier, so is one element more, is transported in your data streams, it has a low impact on latency apart from the taking the snapshot itself. But if that happens asynchronously, it's not a big deal either. Okay, since I can tell you a lot of things, let's take a look at some small experiment we've run. Here we have grouped some strings. We had a string source which generated strings, and we grouped them to compute some summaries and counts for them. So this means this grouping means that we had a shuffle operation. We executed this experiment on a Google Compute Engine cluster with 30 nodes, I think, where each node had 4 cores and 15 gigabytes of main memory, I think. And first we run the experiment with no fault tolerance at all and measured the number of events which have been processed in total by the system. And we achieved a throughput of roughly 86 million events per second. And we did the same experiment with exactly one semantics. So we turned on the fault tolerance, and we observed that the performance only dropped slightly to 82 million events per second. As a comparison, we also ran the same job with Storm, and we found out that we could achieve a throughput of 310,000 elements or events per second. To be fair at this point is we used the vanilla Storm system, so we didn't do any tuning, so I'm quite sure that we could still improve the results. However, I doubt that one could improve the results by 2 magnitudes of order. Okay, is the job done now? So we've seen how to draw checkpoints and how to recover from them. Is that enough to cover all possible failures with Flink? Well, in fact, not completely. If we take a look at the current architecture of the system, we see that we have multiple task managers, which are responsible for the executing the actual work, and one job manager, which is responsible for orchestrating the work, distributing the task to the task manager, and accumulating the results, for example. The thing is, there is only one job manager. So what happens if he fails? Well, your cluster stops working because there's no other job manager which can take over. So obviously, then even checkpointing won't help you because the cluster stops working. What we did is we made the job manager in the upcoming release 0.10 highly available. There's a mode. If you start with a Flink with the HA mode, then multiple job manager are started, and we use Apache Zookeeper to select one leader among all started job managers. This leader is then responsible for the execution, for the management of the cluster, let's say. And all other job managers become standby job manager to wait for a failure of the leader to take over. So if that happens, then the standby job manager are notified by Zookeeper that the leader died, so that a new leader has to be elected. This is then done and told to the task managers. They will reconnect to the new leader, and everything continues working. Okay, so we solved basically the problem of the single point of failure in our architecture. However, I haven't told you yet how the new leader is able to retrieve the jobs which have been executed before. That's also done via Zookeeper. So what is happening when you submit a job to the job manager is that first of all, the execution graph for the job is generated, and it is written to a persistent data storage like HDFS, for example. Additionally, a handle to this state, or to this persisted execution graph, is written to Zookeeper, so that in case of a failure, a new leader can retrieve the execution graph by first getting the state handle from Zookeeper and then reading the execution graph from your state backend. And only after that happened, the job is deployed and executed on the task managers. We use a similar approach for making the checkpoints also available, the completed checkpoints. So whenever a job manager triggers the checkpointing, on the task managers. Then the individual operators create a snapshot of their state, like here. Then next they will persist it to some state backend and send the handles to this state back to the job manager. At the job manager, we accumulate the state handles to create a global checkpoint. This is again persisted to some state backend, HFS again, and we write a handle to this accumulated checkpoint to Zookeeper, from where it can be retrieved by the new leader as well. And that way, we can deal with failing jobs in general. So this brings me to the end of my presentation. What you've seen, or what you've seen today in a nutshell is that if you use Flink, you will feel less like her and more like him when you enter your office in the morning to check on the progress of your jobs. Flink gives you, now with the upcoming 0.10 release, a job recovery mechanism which gives you still the freedom to tune your job for throughput and latency. And at the same time, it guarantees you exactly once semantics if you need them. And with the high availability of the master, there is no longer a single point of failure, so that Flink will always keep processing your data, no matter what comes. And with that, I'd like to thank you for your attention. And if you have any questions, yeah, feel free to ask me.
Hey, I realized that for user-defined functions, you have to write extra lines of code to restore the state of the counters. But for example, in Hadoop MapReduce jobs, you don't have to do it. So if the task is retried, so you can continue counting. So any reason for that? And maybe is it at all possible to make it somehow automatic? And also, what kind of other user-defined state do you have to annotate your fields with? Because now you have to use this state operator, right?
Operator state. Yeah, exactly. The moment, well, the system has to know somehow which state it has to checkpoint, right? A priori, this is not so easy to extract from an arbitrary Java class. So for the sake of simplicity for the moment, we have this operator state, which the type which you have to use. But in the future, it's also conceivable to do it with annotations or to some extent, I guess, also automatically, but then you can also, I mean, sometimes it might be the case that you have some state in your user-defined function, which is doesn't have to be checkpointed, and that to distinguish from the state you want to checkpoint automatically is not possible so easily, I guess. Yeah, I mean, here, well, but I mean, you just would see like a long value if you didn't wrap in this operator state type, or if you didn't annotate it with some annotation. Then if you see two long fields, for example, the one is used as the counter and the other one is a helper thing, which is not necessary to checkpoint. How do you distinguish? That's not so easily possible. So I guess in the near future we will have some annotation, and so far we have this operator state type. Yeah.
How do the snapshots work exactly? Like, do you track which data changed and then only update this to the snapshot server, or do you always send the whole state, which would be bad for something like materialized views or so, right?
Yeah, the plan is also to support incremental snapshots, so that you basically store the diff. The country, I think it's the whole state, that basically this operator state is then serialized and that way retrieved. But well, goal for the future is to offer also, as you said, it might be costly to transfer like a huge map of something where only some element or some entries have changed. and to store it all the time on the state backend. For this incremental snapshots, well, this will be added in the future.
And another question: have you thought about, like, also in the future, integrating something like a small in-memory database in the processing elements, like Samza does, apparently?
We haven't made any concrete plans about that. It might be, probably it's not a big deal since we have the state backend abstraction to plug in the in-memory database, but then you lose to some extent the persistence guarantees when the task manager, for example, dies. Then if it's only stored in memory, then it's like array, right? But depending on your needs, it is then configurable. You simply just pick the right state backend for your usage.
Yeah, but you could like snapshot that as well, like the state
yeah,
of that if you like combine it. I think that's how Samza does it.
Okay, well, yeah, that would be like a meta checkpoint, right? Like. Yeah, but there are no concrete plans yet to implement it.
Yeah, can you comment on the local recovery possibilities? Currently, the recovery looks like a global, like a whole topology has to be redeployed. Yeah. Can you think of local operator level recovery? Like an operator dies, can you just recover that operator without redeploying the whole topology?
Well, at the moment, when one let's say instance of the operator dies, it will make the whole job fail. So it has to be recovered completely. However, it doesn't have to stay that way. It's just the way it's currently implemented. You're right that if the system notices that a single element has failed, then it should be, well, it's theoretically possible to just restart this one and hold the others for the moment. But at the moment, a failure at any task will make the whole job to be restarted, but from the latest completed checkpoint. Yes.
So how are you transporting the barriers? I mean, if you're using, for instance, at most one semantics and you lose a barrier in the data stream.
Well, for at most once, this is basically the equivalent for turning checkpointing off. So there are no barriers injected in the data stream between the operators. And in case you have checkpointed the fault tolerance mechanism activated, then barriers are simply elements which you push to your data stream, which are transported like any other element. Of course, the system distinguishes them from normal elements to the operators. So.
And with the opposite case of at least once, if you get two barriers or more.
Well, one barrier is uniquely associated to one checkpoint. So there's a checkpoint ID associated with an ID. In the at least once scenario, the difference from the exactly once scenario where you block the channels for which you've already received the barriers in order to wait for the other inputs to receive the barriers, it is that you continue processing the elements coming from the inputs where you've already received the barrier. And once you notice that you have received from all inputs the barriers, then you can emit a new barrier for to your downstream operators. However, since you've processed elements from which belong actually to a later checkpoint, your state will contain this information when you checkpoint it for the previous checkpoint. So that's where the at least one semantics come in. Yeah. So it might be that on one channel you have like two, like a barrier for checkpoint N and a barrier for checkpoint n+1 in the at least once scenario. And if from a second input now you receive the barrier for checkpoint n, then you will emit a new barrier for checkpoint n, but still you will have one barrier waiting on the first input, which waits for the checkpoint barrier n+1. And then once this has received, barrier n+1 will be sent to the downstream operators. I hope this made the thing a little bit clearer.
Last question. So it sounds nice with having super good performance and all these different configurable guarantees, but often I think we see these developers of these frameworks like Flink and others that they have these promises and they can argue theoretically how this should work, and then we see some guy on the internet, usually it's the same guy, testing these frameworks, and then they fail in some kind of assumption, underlying assumption that usually breaks. So my question is if you are also testing these assumptions, so are using some tool like Jepsen to simulate network partitions and similar conditions to see if it actually works out in practice?
Well, at the moment it's a brand new feature. What we want to do is having like a chaos monkey test, where we basically have a streaming job which well, is continuously working, and we randomly kill task managers and job managers to see whether it can recover from it. Since, well, it's the release 0.10, and we are still working on it. We haven't set up this test, but we will definitely do it, because yeah, as you said, one should make sure that things actually do as one says. Yeah.
I think you can see this more as a CA system, in the sense that there might be a case of the network partition where you have two job managers and task managers somehow connect to the wrong one, and all of a sudden you have two clusters. So I think this is a possibility here.
Thank you.
Okay.